Hi, everybody. Welcome to our asynchronous lecture for Wednesday, June 3rd, 2020 for the summer session. We're going to change things. We're going to go from one topic that's been the first two modules, which is kinematics, and we'll then move to dynamics of Newton's law. So to give you a sense of what we're trying to do, I want to kind of make a conceptual map here. This is the kind of thing I would in the past sometimes do on the very first lecture of the class. So it's a step back, but there's also something to be said for just jumping right in. So once you've jumped in, maybe it's a little easier to see where we're going and what we are doing. So this is a physics class, but it has a topic, and the topic is mechanics. So this is the study of classical mechanics, which is to say the field of mechanics, the description of the universe of in a certain context that is over 400 years old, but fairly well sophisticated and continually developed up through really the beginning of the 20th century. And the focus of this is the study of motion. So when I say mechanics, what a physicist means is the study of moving things, of the fact that things move and what we know about them. And that study can be broken down in very approximate terms into two major subcategories. So the first subcategory is what I will call the field of kinematics, which is what we've basically been doing for the first two lectures of the class since the beginning of the class. And in this particular, this is the emphasis on how things move, right? And kinematics is a rich subject at some level. We've begun to look into it. So what have we learned? We've learned about 1D kinematics, ideas of position and velocity and acceleration. We've now looked at 2D kinematics, and we've looked at uniform circular motion. We've looked at projectile motion. And we've looked at, vectors, right? We've looked at I hats, J hats, and so forth. All of this stuff, everything that we've done so far is on this side of this conceptual map corresponding to our understanding of physics, our understanding of mechanics. But, and one of the reasons that we take some time and energy in this is because we need a precise mathematical language to describe motion, and we have to develop that first. By the way, there's a whole third branch of kinematics, folks related to rotations that we'll deal with coming up later in the semester. But for now, we're going to jump to the other side, and we're going to look at a subfield which is known, which I call dynamics. So when we say dynamics, what we're interested in is why things move. In other words, what are the underlying causes of motion? In other words, this is just describe the motion in a mathematically sophisticated and careful, accurate way. But this is explain the motion. Understand. Please explain why things actually move. What are the rules for why things actually move? What causes things to move? Once you understand those rules, can you explain those motions? Can you predict those motions? And dynamics has two major forks, at least for this course. And one of the forks is what we're going to call Newton's laws. So Newton basically came up with a system of explaining motion, his laws, and we're going to look at that. Now, it turns out there's a mathematically equivalent, but conceptually distinct set of descriptions for mechanics, which we're going to call conservation laws. So you've heard of these before: conservation of momentum, conservation of energy, conservation of angular momentum. It's possible to go back and forth between these two descriptions of the causes of motion. It's not actually the case that you can point to one or the other, at least not in the classical view, and say that this is more fundamental than that. But historically and conceptually, we're going to start with this path, with Newton's laws, and then see how far we can go. And you'll see, in principle, we can go quite far with Newton's laws, but the formulation, the alternate formulation, which we can call conservation laws, turns out to be very powerful, relatively effective for solving other classes of problems. So this is the map, and then everything we do in detail for solving problems is basically subtrees of these branches on these major modes. So why is this conceptual map important? It's important because every time you pick up a problem, how do I put it? The goal of the class is for you to understand this conceptual map, understand what is in each of these boxes, and to be able to demonstrate your understanding by applying that understanding to problems and solving them. So the only way, I can't put it, I can't look inside your head. I can't say, oh, this student, the way you think about dynamics and Newton's laws is the right way, and you therefore understand, and that's our goal. Our goal is that you understand what Newton's laws are. But the only way we can assess the extent to which we've succeeded and you've succeeded at understanding Newton's laws is to ask you to solve problems. So that's why this is a problem-solving class. The goal is actually not, I'm going to say, in some sense of the word, your goal as a student is to successfully solve problems. But the reason that's your goal is because that's the mechanism by which you demonstrate understanding. Those problems are specifically designed to test your understanding. So until you understand these concepts, you can't do the problems. I think that's the way I'd like to put it. And then when students say, I understand the concepts, but I can't do the problems, what they really usually mean is they don't really understand the concepts, and therefore they are not prepared to do the problems. So let's focus on the concepts. And then if we work as hard as we need to understand the concepts, we will find ourselves well equipped to solve the problems and to demonstrate that understanding. So I want to introduce you to Newton's laws. They're both profound and simple at the same time. There's three of them. There's 3+, okay? So when I say Newton's laws, what I really mean is a system of statements that was put forth by Newton that can be expressed in compact mathematical form. Okay, so the first law, sometimes known as the law of inertia. How can I put it? This is an important law, but it's also, it's not a law that we can use very well. It's not a law that we can test your understanding of by actually solving problems. It's basically, how to say, you learned it when you were in high school. The high school version of Newton's first law is that objects at rest stay at rest, and objects in motion continue to stay in motion. That's a pretty imprecise and useless law. Let's make it at least a little bit more useful. The basic law says that if the net force, and this is a thing we have to contend with, if the net force on a particle or system, it turns out, doesn't matter, is equal to 0, then the velocity of that object is equal to a constant. That's what it says. So let's get back to the first law in just a second. The second law, now in this class, I'm going to highlight and exaggerate everything I can about Newton's second law, because if you ask me what the whole point of the course is, I'll say the whole point of the course is to look at Newton's second law and figure out what it means and how it applies. That's Newton's second law. F equals ma. But F equals ma is not quite what I've written. I've written F net. So we have to deal with this thing called the net force. And then we have to deal with this M. And then how can I put it? This is, in some sense of the word, the easiest possible equation you could write down. Something is equal to two other things multiplied together. And this equal sign is subtle. So let's unpack this for just a second. So again, this is my favorite equation. Remember, when I write questions and problems in this class, the primary goal is to see if you understand a major concept. If you I'll give you this advice. If you encounter a problem and you don't know how to proceed, the first thing to try is to ask yourself, well, can I apply Newton's second law to deal with this? Because the chances are that I will find every opportunity I can to ask you a question or give you a problem dealing with Newton's second law. It's by far my favorite equation for the whole class, okay? So let's look at what we have on the right side. On the right side, we have this thing called M, which is the mass. And mass is one of those things which is, it's hard to define, but we know it when we see it. It's basically how much stuff there is, where that stuffness is measured by basically counting the amount of stuff and, in some sense of the word, assessing it in the context of this thing. If I have a whole bunch of atoms and I count them and I know what the mass of each atom is, I can add up all those mass to total mass. So it's a thing that matter has. It's a property that matter has. That's cumulative and additive, which is to say, when I take a bunch of mass and I put it together, the new thing has the same amount of mass. So without getting too worried about what that thing is, let's just call it the mass. This thing, well, we know exactly what that is. That's the acceleration. That's the kinematic quantity that we've already wrestled with. It's the second derivative of the position. This thing here, F net, is defined as the vector sum F1 plus F2 plus F3 of all the actual forces that are actually on that body or on that system, okay? So we have to make it clear what we mean by these forces, but here's the important thing. This thing here, the net force, is not a force. It's the sum of all those forces. And by the way, there might be one force, in which case F net and F force are the same. There might be a whole bunch of forces. There might be zero forces. Whatever it is, they all add up together. And by the way, these are vectors. So they add tail to head. They don't add like numbers. You don't, 1 plus 2 is not equal to 3. You have to actually add component by component all of these different vectors the same way you would do it. So that's the second law. So there's one more subtle thing I want to say about the second law, and this is why it's so profound and so powerful. The thing on the right side is not the same as the thing on the left side. I'll say that again. The thing on the right side is not the same as the thing on the left side. They have the same value. They're equal in value. That's the law. It is the law that if you have this thing and you have this thing, they will have the same value. They will both be, this times that vector is the same thing as this vector. They are the same, they have the same quantitative amount, but not physically the same thing. This thing is a multiplication of some strange concept called mass times a kinematic quantity, which is defined by the motion of the body. This is the forces on the body. So the reason this is a dynamics equation is because this equation doesn't just say this is equal to that. What this equation says is that the causes of motion, and in particular the cause of acceleration, is force. Force is what makes things accelerate. That's what the second law says. This is not just this equality is this equal sign is way too flimsy for this equation, because in math, if I say this is equal to that, you can swap it around. It's just two things are the same. That's just an equality. They're functionally equivalent. That's what equals means. But here, these two things are different. They're different physical quantities, right? It just happens that they're related by the fact that they happen to have the same value. It's kind of amazing. You could have written it F is proportional say where that proportionality constant is determined by the properties of the body, which is whose value is m. That would be also fair to say. Okay. And then finally, and we'll give up on this. Below it is the third law. The third law. So what I tell students is that Newton's third law is powerful and dangerous, kind of like dynamite, because you can do some amazing things with it. In fact, without it, there's certain problems you can't solve, but it's easy to misapply. It's easy to go wrong with Newton's third law, even though it can be written very, very simply and very, very straightforwardly. It's conceptually challenging in the sense that it's easy to get it crisscrossed, so to speak. So what does Newton's law say? Newton's law says that anytime you have one body, so here's a body right here, and anytime you have a second body here, anytime there's a force of one body on the other body, it doesn't matter what kind of force. Here, I'm pushing my one fist against the other, right? Anytime there's a force on one body due to on the other body, there must be an equal and oppositely directed, equal valued and oppositely directed force on the other body, right? So you always hear it's the law of action and reaction. That's not helpful. I don't like, there's no action or reaction in this class. There's forces and force pairs. So what the third law says is that if there's a force on body one due to body two, so when I write down F12, this means the force on body one due to body two. That there must also be a second force, which is the force on body two due to body one, and their magnitudes are the same. Now, by the way, if you learned in high school that there should be a negative sign here, don't do that. This is an equation of magnitudes. Magnitude of this force is equal to the same as the magnitude of this force. And yes, they point in opposite directions, but this is not a vector equation. This is a magnitude equation. This number, which is positive definite, right? If it can't, there's no such thing as a negative magnitude. F12 means the magnitude of the force on 1, 2. In other words, another way of writing this equation, a totally equivalent way of writing this equation, is that the force 1, 2, its magnitude is equal to the magnitude of the force 2, 1. So obviously these are both non-negative quantities. Okay, this is the second law. This is the third law. And again, this is powerful and dangerous. It's dangerous because you have to figure out which force if you're going to use this equality and you know this and you want to find out, or vice versa, you'd better figure out which forces go from one side to the other. And the trick is that we're going to use these indices. Basically, flipping indices is going to be the technique that we're going to use. Every time we work in this class, every time I have an index, I'm going to be consistent. The first index is the force, is the body that the force is being applied onto, and the second index is the force is the body that the force is due to. So remember, anytime I say F12, I have on and then due. So I just think on due. F, the force on body one due to body two, is equal to the force on body one due to body two. On due. Okay? So for the next really 2 or 3 lectures of for today, for Thursday, and a little bit of Friday, we're going to spend all of our time mostly applying this equation, the second law. Yeah, it's our favorite. And then on occasion, taking this somewhat dangerous piece of dynamite out and applying the third law so that we can solve problems using this expression. So we're basically going to use these expressions to figure out what's going on. All right. I've got one more short lecture to give you on the force menu, and then we will be done for today.